Momentum assignment, level 4. Now it's level 4, so don't panic. I'm going to mark them just like I do as regular levels. So if you don't get this perfect, you don't have to panic. The idea here is to do the best you can and see what you can do, right? You know me. I'll take good care of you. Okay. The first thing is this. You have this ball, and it's moving this way at 20 meters per second. This is the first question. And it's going to collide with two balls that are sitting like this. Okay. The first thing we want to sort of think about is, and I was looking back at all the videos that I had assigned to you, and I'm not sure if this concept came across very clearly in those videos or not. And I haven't made one specifically for it, but it's the idea of what we call an elastic collision. An elastic collision is a collision where, like all collisions, momentum is conserved, which means this statement is true. Now, this is how most collisions work. They are not elastic. This is the only thing that's true about them. But the other thing that's true in an elastic collision is that the amount of kinetic energy is also conserved. So that means this is also, also an equation you can use. So you can do m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. But you can also generate the kinetic energy equation where the kinetic energy of the first object plus the kinetic energy of the second object is equal to the kinetic energy of the first object after, so we v prime it squared. It's kind of a little bit messy. 1/2 mv2 prime squared. Okay, that equation also works. Now, because these balls are all the same, the nice thing is that the masses will all cancel in this equation, and the halves and the masses will all cancel in this equation. So we're left with two relatively easy equations. V1 plus V2 equals V1. Well, actually, to address this particular question, let me rephrase that. I was just speaking kind of generally here. But in the question that we actually have three balls, right? So if we added all three balls in, we would be left with we'd be left with M1. Sorry, M's canceled. Start again, Mark. Okay. Here we go. We will be left with V1 plus V2 plus V3 equals V1 prime plus V2 prime plus V3 prime. That's from this equation. And we can put numbers in there and we can work stuff out. Now the other thing we're left with is from the second equation, V1 squared, because this comes from the kinetic energy equation with the halves and the m's canceled out, also equals V1 prime squared plus V2 prime squared plus V3 prime. These are the afters. So this is a second equation we can use in collisions, and I don't know if that came across in the videos or not. You can only use it when you have an elastic collision. Most collisions are not elastic, but many are near enough to elastic that you can do this. This particular question doesn't say it's elastic, but you have to assume it's elastic to work through it. And at least I think you do. I can't remember for sure. We'll find out in a minute. Anyway, that's something that you can consider. Okay, go back to the picture now. Here's where everybody gets messed up on this question. They see this ball and they see that it's going to strike right in the middle. And they assume that when that ball hits here, these two guys are going to fly off at 45 degrees. But that is incorrect. To figure it out, we have to put that ball up next to the other two balls like this at the moment it hits. And then what we have to do is remember that the balls will act on their centers of mass. So if you draw the centers, and we have this sort of the line that the ball was coming in on. Well, that's not a very good picture, is it? Start again. Should have drew the reference line first. Okay, let's do it right. Here's the reference line. So one ball is here. The other ball is here, and the third ball is here. Put their masses in here. Connect. This mass will push on this mass and push this ball this way. And this mass will push on this center this way. Look at those. That's an equilateral triangle in there, isn't it? And all the angles in an equilateral triangle are what? 60 degrees. So this is a 60-degree angle. It's not a 45 or a 90. So what you have to do then is when you resolve this, those two arrows for those afters will have components, right? They'll have a component this way and a component this way. This will be the x component. This will be the y component. And the angle in there will be half of 60 or 30 degrees. And the other one will have the same thing, an x and a y with an angle of 30 degrees, because you're going to have to do the components of those. Okay? So that's the first problem, making sure that you get that angle right for the after part and the directions they're flying off in. Here's the second hint for this question. Instead of doing this, P total equals P total prime, before and after, because you have components, I want you to think that this is the same as doing the total x only components, and then also doing the total y components. So what's going to happen here is one of these equations, I think it's this one, is going to give you a tidbit of information that you can then use back in this equation to help you get where you want to go. So think about this. Here's what you've got. You've got the three balls. All right. So the first ball is moving along this line, which is the x direction. The other balls have an x and a y component, but the y components, this way and this way, are symmetrical. And they're going to basically be equal to each other, aren't they? In opposite directions and cancel out, so to speak. So they're not really going to have much effect. So really, when you look at this question, the only thing that really matters is what's happening in the x direction for all these balls. And so that's why this equation is going to be the one that's going to pop out your solution. So give that a whirl, mess with it as best you can, see what you can come up with. You're going to look at that equation and those equations. And don't forget, you can also use kinetic energy if you have to. Okay, I'll let you hammer away at that. And maybe I'll give you some more hints later. Maybe not. It's hard to say. The expectation here, of course, is that you're all helping each other out somehow via the social media network. So it's kind of like a group effort anyway. So do what you can. And yeah, there we go. Number 2, the man on the ladder. Here's the ground. Here's the balloon. And here's the ladder. Okay, this is my hot air balloon here. Whatever that's supposed to look like. Okay, problem here is reference frame. It's a very simple question once you figure out the reference frames. Because it talks about the speeds of the balloon and the man, but it talks about speeds relative to the ground, and it gives you a speed of the man relative to the ladder, which messes things up. Got to make sure that all of our velocities are in the same reference frame. So it's a simple momentum question with total momentum before and total momentum after. So we have the velocity of a balloon and the velocity of a man before. And then, of course, there's a velocity of the balloon and the velocity of the man after. So put primes on those. Now, apparently, the balloon and the man are initially stationary relative to the ground. We're talking about vertical motion here, right? So they're not rising or falling. So we have a 0 here, and we have this here. Good. Here's the problem. They're telling us a 2.5 is the velocity of the man after, but that's relative to the ladder, not relative to the ground. So what does that actually mean? Well, I want you now to think about, here's the ladder attached to a balloon. Okay. And there's a man on it. What's going to happen, believe it or not, is if the man starts to climb, his velocity will change. And we can see from this equation that if this changes, then this can no longer be 0. In other words, there has to be well, in order to keep it 0, I guess to keep it from changing, let's say this goes up and increases, this is going to have to decrease. So by starting to climb the ladder, what actually happens is the balloon itself must move in response to the man climbing upward, and the balloon must begin to move downward, because the two of them have to balance out. They have to work out to a 0, right? So you can think of it this way. If 0 is 0 plus 0, well, that's no problem. But if you change this to something going up, you have to change this to something going down to keep it 0. So the balloon is actually going to rise or fall, in this case, fall. All right. Now, if you're on the ground watching this relative to the ground, you can see the motion of the balloon relative to the ground, no problem. But as the man begins to climb up the ladder, what you see is a combination of his climbing speed, the velocity of the man relative to the ladder, but you also have to understand he's attached to the balloon, and so he will also have a velocity from the balloon, won't he? He will also have the velocity of the balloon. So the velocity of the man relative to the ground is equal to his velocity relative to the ladder plus his velocity of the balloon. This person would see both movements, the climbing and the balloon. So we need to recognize this in order to solve this question. Then we can set it up nice and easy. Total momentum before, total momentum after. And you're going to have the velocity of the man and the balloon being 0. Then you're going to have the velocity of the man. The momentum, not the velocity. Momentum's part of it. Let's put momentum in there because they have different masses, obviously, right? So it's the momentum of the man plus the momentum of the balloon. But these have to be measured from the ground. So 0 equals m of the man plus the velocity of the man from the ground plus mass of the balloon plus the velocity of the balloon. Well, going back to here, you can see what has to happen, a substitution. We have to put inside here mass of the man. He's 80. He's a big man. This is going to be a substitution. Velocity of man relative to the ladder plus velocity of balloon. That's what I got up here in the box. Remember? Right there. This is the same. The 2.5 is this number. The mass of the balloon is also given, so I could have written the 320 in there. And you can see now that all you have is a V balloon that needs to be dealt with. And of course, this is after, and this is after. These are all afters, right? And so the velocity of the man after. Okay, you should be able to crank that out from there on in. So those are the hints. Try to get that assignment in as quickly as you can. The sooner you get it in, the sooner I can add it into your marks. I did do the marks